If this hot wire touches the ground wire, the circuit breaker instantly trips. If the hot wire touches the neutral, it also trips. But if we place a lamp between the hot and the neutral, it doesn't trip. When we turn on a light switch, the current flows along one of the two service hot conductors to the property, then down through the electrical meter, then through the main disconnect, and then into the main electrical panel where it connects to one of the hot bus bars. It travels down this bus bar to the circuit breaker, and then along the hot wire to the switch, and then to the light fitting. It then travels back along the neutral wire to the neutral bus bar, and then back to the main disconnect, then back through the meter and over to the transformer. The circuit is complete, so the light illuminates. Now, I have animated this using DC current as it's easier to visualize, but in reality, we're using alternating current, which moves backwards and forwards like this. If we measure between the hot and the neutral, we should read around 120 volts. The resistance of the lamp limits the current flowing in the circuit, and so only a small current will flow. This is much less than the rating of the circuit breaker, so it will not trip. If the hot wire came into contact with the ground wire, there would be almost no resistance, so an extremely large current would instantly flow. This would exceed the limit of the circuit breaker, and it will automatically trip to protect the wiring in the circuit. But all the other circuits in the property should remain energized. The NEC defines a ground fault as an unintentional connection between an ungrounded conductor and a normally non-current carrying conductor, including enclosures, raceways, equipment, or earth. When the fault occurred, it allowed current to stray from the intended path and traveled along a normally non-current carrying conductor back to the source, in this case through the ground wire. This is therefore a ground fault, and it means we have a serious problem with our circuit. The NEC defines this as an effective ground fault current path because it's intentionally constructed for fault currents to return to source. Ground faults occur when the hot touches the metal surface of a switch or an outlet, or if it touches the metal electrical box. It happens when a nail or screw is driven through the cable and connects the hot and ground wires, or when a liquid enters the electrical box and provides a passage to ground. Or maybe the insulation of the wire in a device has been damaged and the current flows through the metal case to ground. Regardless of the cause, if we try to reset the breaker, it will instantly trip again. If the fault occurs from a plug-in device, we can just unplug this and the breaker should reset. We then need to repair or replace that device. If the fault occurs from the fixed wiring within the walls, then we need to check the connections to ensure they are all properly fixed and dry. If that doesn't solve the problem, we need to work our way along the circuit, disconnecting sections until the breaker allows the reset. We then know that the fault must occur somewhere in the disconnected section. We can use the continuity function on a multimeter to confirm whether it's in the fixed wiring or within the fixture, as there should be no continuity between the hot and ground. The reason the breaker trips is because the wires will increase in temperature any time current flows through them. This is normal, it happens every time we turn on a device or a light. But if the wire becomes too hot, then the insulation will deteriorate. This will expose the conductors and potentially cause a fire or present an electric shock risk. You may have noticed that there is also a path current can take from the ground rod of the main disconnect to the ground rod of the transformer. This path has a much